When we estimate the area under a curve, we sometimes directly use the integrals, and sometimes we approximate using different approaches of Riemann sum. The three major approaches that are tested in AP Calculus exam are LEM, REM, and TRAP. So let's take a look at this problem, which asks us to approximate the integral x squared plus 2, lower bound x equals 1 and upper bound x equals 3, using four subintervals, with given x values and y values in the table. Now let's examine these three different graphs corresponding to LEM, REM,
When we're
and
asked
TRAP.
to use LEM, we estimate the area under a curve by adding up these four rectangles, and since it's LEM, we are using the height on the left of the integral as the height of the rectangle itself. Since the width, which is the difference between the x values, is 1/2, we solve for the areas of the four rectangles by multiplying width and height. Summing them up, we have the area under a curve. Notice that there is some space between the curve and the rectangles, so the number we got is actually smaller than its true value, so we say that it's underestimated. Second, when we're asked to use REM, we estimate the area under a curve also by adding up four rectangles, but this time we're using the height on the right. We again multiply the width and height of the rectangles and add them together, while this time we can see that part of the figure goes over the curve, so the answer we got is actually greater than its true value, and we can say that it's overestimated. Lastly, when we're asked to use TRAP, the approach is different from LEM and REM, as we're adding up the areas of trapezoids instead of rectangles. So we're using both the y value on the left and the y value on the right, and we're multiplying the sum of them with the difference between two adjacent x values, and again multiply by 1/2. And here we have the area of one trapezoid. Repeating the steps and adding the areas of all the trapezoids together, we're able to have a more accurate approximation of the area under curve than LEM and REM do. But when we look closely, it still goes slightly over the curve, so we still can say that it's overestimated. Let's take a look at this AP free response question. Besides the more common REM, LEM, and TRAP, we have another way of solving Riemann sum, which is the midpoint Riemann sum, which has been rarely tested on. However, part A of this FRQ requires us to use midpoint Riemann sum with three subintervals to determine the area under curve. Let's look at this graph. Basically, midpoint Riemann sum is pretty similar to REM and LEM, despite that the height is the average value of two adjacent y values. For dividing the sum of the two y values by 2, we have a height to use. Afterwards, we just repeat what we've done for REM and LEM. We calculate the areas of each small rectangles and add them together. In this case, we're provided with 7 values, which can make up 6 subintervals if we use every single one of them. However, we're asked to only use 3. So after grouping them into 3, we can see that the second set of data in each group is actually the midpoint and its height. How interesting! So instead of inputting a lot of work, we just multiply the second y value in each group by the constant width, which is 2, and add all of the sub-areas together. We're left with the answer of part A.